session. The first talk is by Professor Dimitri Roditchev. He will report about proximity phenomena and superconductivity in labs on silicon in nanofilms with monolayer thickness. Okay.
Okay, you can go 25 minutes plus 5 questions.
Okay, thank you very much, Mr. Chairman. Thank you, organizers. Before I do my talk, I would like to do some advertisement. Please do not fly EasyJet anymore. So, this talk will be devoted to proximity phenomena and superconductivity in the single atomic layers of lead as deposited on silicon. The talk is related to our experimental work made in scanning tunneling spectroscopy, but also supported by many collaborations with American people, Russian people, Spanish people, and etc., which are cited on this first slide. Next slide, please. So, before I start, I would like to say a few words about Professor Chudinov, who was appointed in Kamerina University for several years and who was a PhD advisor of my PhD thesis, but also a good friend and advisor and organizer of science of many researchers also sitting in this nice place, Ducal Palace. So on the left top photo, you have a famous photo taken in Kamerina University when Abrikosov came. There is also Sergio Stitza, I know many people, Mancini here, Andrei Varlamov, and just behind Abrikosov you have a person, a very modest person, who is Professor Chudinov. And this is a very interesting photo. Because if you go to the internet, you will not basically find any photo of Chudinov. He was a very modest person, very high ranking researcher, extremely polite, always trying to get a deeper insight in any physical understanding. On the right photo, in black and white picture, you see Chudinov working with young students on a youth physical tournament that he organized in Moscow, but also in Europe, in different countries. And on the bottom photo, you see some people organizing some experiences during this tournament organized by Chudinov. And the right person with glasses is nothing but Professor Buzdin, that everyone knows. You see that his hairs are not gray yet, but rather black. So next slide, please. So Professor Chudinov not only was advisor of many people, he also published many interesting textbooks, and one of them concerning semi-metals. And you have this nice, on the right picture, you have this nice band gap inversion that speaks to many of you about graphene and etc. On the left part of the same slide, I just cite and house the list of people who were concerned by his research and who benefited from his advices and collaborations. Most of these people are now professors and full professors in leading laboratories and universities all over the world. Next slide, please. So this is the outline of my talk. I will. So this work was mainly stimulated by Ginzburg prediction in the 60s, in which he predicted that the surface electronic properties and any surface could be very different from the bulk counterpart, and in principle, the superconductivity may rise, and also high TC superconductivity. And I can tell you that recently there is an archive paper appeared in CONDMAT that showed that a single unit cell of iron arsenide is a superconductor at 100 Kelvin. So the outline here is that we will deposit lead on silicon in very high quality, ultra high vacuum conditions, and we will study the superconductivity in them. Next slide, please. So when you put lead on silicon and clean silicon, which is 7 by 7 reconstructed, you get this specific growth, which is called Stransky-Krastanov growth. Because of lattice mismatch, the lead islands grow. You see them in red, and also you have the silicon surface, which is appeared here as a bright blue, which is covered by a single atomic layer, which is called wetting layer of lead. And this wetting layer may be of very different structural compositions. Next slide, please. In fact, the phase diagram of this monolayer of lead, so you have just a single layer of lead atoms. The metallic phase is situated between 1.0 and 1.4 atoms of lead density as related to silicon density. So at low coverages on the left part of this diagram, you have insulating phases. So you have metallic lead atoms, but they do not percolate and there is no metallic conductivity. But at densities above one single monolayer, you have different phases which are shown here, and all of them are metallic, and some of them are superconducting. And after, when islands grow, you have also bulk superconductivity of those islands. I will just stop for 1 minute describing them. Next slide. Next slide.
Yeah.
So, next slide. We use the scanning tunneling. Next slide. Next slide, please.
Yes.
We use scanning tunneling spectroscopy to reveal the superconductivity through the superconducting gap. As you know, everyone knows that the superconductivity is a quantum process in which you have this gap opening, and the gap is related to the pair function in a very non-trivial way, and the tunneling conductance is proportional to this gap function and folded with Fermi-Dirac distribution. Next slide. So, in order to study these monolayers, of course, you need a very drastic ultra-high vacuum conditions. Specifically, you cannot get your samples outside of the UHV chamber, so you should combine deposition chamber, characterization chamber, and ultra-low temperature STM in ultra-high vacuum. Next slide. So, I start with the superconductivity in islands. Next slide, please. So, these are these islands, and it was a belief that depending on thickness of islands, you will get different superconductivity. Next slide, please. And since depending on thickness, you have a quantum wall confinement effect in these islands, in some positions, in some thicknesses, you will get enhanced superconductivity because the Fermi level will lie in this confinement-induced electronic structure. Next slide. However, it was not shown that there is any enhancement of superconductivity, but rather, with reduced thickness, you reduce the superconducting gap, as on this paper by Brandt et al. Published years ago. You see on the top part of the left diagram, you have a superconducting gap which is large, but when you reduce the thickness of the islands, you get more and more small gap, and finally very reduced gap at 6 monolayers. Next slide. So now we turn to the case of single atomic layers of lead. The first case is amorphous wetting layer. Next slide. So when you grow, when you deposit lead atoms on your surface, the islands grow, and the wetting layer, which is in between them, is not crystallized. It is amorphous, as shows the topographic image on the bottom, small square image B in this picture. The islands, they are crystalline, as shows the right insert of a scanning tunnel in microscopy image showing atomically resolved lead surface on the island top. But when you go, next slide please. So on next slide you see that the islands are indeed superconducting. They are characterized clearly by a superconducting gap, which is about 1.2 millivolt. Very nice BCS gap. But if you go to probe the wetting layer, amorphous wetting layer, you will see a sort of zero bias anomaly with no superconducting coherence peaks. Next, and this anomaly is a well-known anomaly of Altshuler-Aronov, which is related to the correlations, electronic correlation in this diffusive and disordered medium. Next slide, please. So we study the proximity effect between these superconducting islands and this disordered correlated metal, and you see on this three-dimensional plot that when the tip is situated on the superconducting island, you see a very nice superconducting gap, which with coherence peaks, which are plotted in red here. But immediately, when you leave the island and you appear on the proximity layer, then the gap, superconducting gap, becomes proximity gap, and then smoothly evolves in the Altshuler-Aronov anomaly. Next slide, please. So this smooth decrease, as shows this bottom map, is not really uniform. You have the general trend of smoothing and reducing the proximity gap when you leave from the superconducting to correlated two-dimensional metal, but yet you still have some special fluctuations, which are very complex to account for. Next slide, please. So we accounted for this correlation effect, taking into account the material, this disordered layer, as a network of resistances and capacitance. And in this way, we were able to fit zero bias anomaly with a single resistance and single capacitor, effective resistance and effective capacitance. Next slide, please. Introducing this, we implemented so-called PE function. I cannot stop too much to discussing this. And let's go to next slide. And again, next slide. And again, next slide. And with this, in this way, by implementing this formalism, taking into account both the proximity effect within Usadel formalism and the Altshuler-Aronov effect within this PE function approximation, we were able to generate on the left plot theoretical curves of the evolution of proximity spectra, which are very nicely reproducing the experimental data on the right plot. And all this with only one single parameter, which is related to the diffusion coefficient, which is drawn just below the point. So let us go to the next slide. And now I turn to the case of crystallized wetting layers. So amorphous wetting layers are not superconducting, but correlated metals. And probably the reason why they are not superconducting is related to the Coulombic interaction that do not allow the superconductivity to settle in. But if you crystallize this wetting layer, you can crystallize different structures, and most famous are square root 7 by square root 3 and so-called striped incommensurate structure. I believe that Professor Hasegawa, who will come give a talk just after my talk, will devote his talk to the proximity effect in this crystallized square root 7 by square root 3 layer. Next slide, please. So it was recently reported in 2010 that these two layers, single monolayer of square root 7 by square root 3, but also this striped incommensurate lead, also single monolayer, are superconducting. Next slide, please. There is a superconducting gap in this material. If you look how this superconducting gap closes with temperature of on the left bottom and central bottom plots, you understand that these materials are superconductors with a critical temperature which is about 1.5 Kelvin. Next plot, please. And this superconductivity is real macroscopic superconductivity in the sense that if you run transport measurements on macroscopic samples, you can really see the resistive transition towards zero resistant state. Next slide. So now we focalize on this striped incommensurate monolayer, which is superconducting below 1.6 Kelvin. So, next slide, please. On the left upper part, we plot a topographic image in which we have a superconducting lead island, so thick island that we call S1, with a superconducting critical temperature of 6 Kelvin. And on the bottom part, you have this crystallized wetting layer, which is superconducting below 1.6 Kelvin. And so, with this the same, so you have this lateral junction between two different materials, and you can play with temperature, and you can realize the situation in which the junction is type S1, S2, so you put in contact two different superconductors, or at a higher temperature, you may have the island still superconducting, but the wetting layer will be already in the normal state. So, at low temperature, when both materials are superconducting, you have the special proximity effect between two superconductors having different gaps, and the evolution of the density of states is plotted on the left bottom image. You see that when the tip is situated on the lead island, the gap is large, and then it gradually evolves to the small gap which represents the superconductivity in the wetting layer, in this crystallized wetting layer. On the right bottom plot, you see how zero bias conductance evolves in this situation, and also different features. For instance, we show that you need to consider consistently the gap function as a function of position in order to account for the spatial evolution of the proximity effect within a one-dimensional Usadel model. Next slide, please. In next slide, I show exactly the same situation, but at the temperature at which the superconductivity in the wetting layer is suppressed. However, the fact that this material is not really a normal metal, but a material in which you have superconducting fluctuations leads to a special evolution of the proximity effect, which is different from the pure case of superconductor normal metal. And unfortunately, I have no time to stop more here, but in the bottom, you have a reference. It's a recent PhysRev X paper we just published, and we clearly account for this induced superconductivity in the neighboring layer between this large superconducting island and the material which will become superconducting at low temperature. Next slide. So, now I turn to the superconductivity on square root 7 by square root 3. Next slide. As I told you, these are atomic layers, and you really need to control on atomic level the structure. First of all, you have to be sure that the material on which to deposit your lead is perfectly reconstructed 7 by 7 silicon, because otherwise you will have no stabilization of square root 7 by square root 3. So here you have on the left panel you have atomic resolution image and large scale image of silicon with atomic steps that you see. And on the right panel, you see the same material, the same sample, covered with a single atomic layer of lead. And what you see that near the steps, the corrugation increases. Please, next slide. And this corrugation is due to formation of some particles in which you have a mixture of lead and silicon atoms. Next slide. So, this is a very interesting result in which we compare the superconductivity in striped incommensurate structure, which is upper part of this slide, and this square root 7 by square root 3 structure, which is bottom part. On striped incommensurate, you get a superconducting gap. You can clearly see, and the superconducting gap is spatially very robust. You see that at zero bias conductance you have no states, and it is completely fully open superconducting gap. However, you have a quasi-particle peaks that spatially vary, and this variation is represented on the top right map, in which high quasi-particle peaks are represented in red and low quasi-particle peaks are represented in blue. And you see that there are special variations of those quasi-particle peaks, and the most striking effect that this special variation takes place almost on atomic scale, on the scale much lower than the coherence length. And this is quite surprising, because in the superconductivity one doesn't expect such fluctuations to be present on a very short atomic scale. In square root 7 by square root 3, when it is desorbed, you have much larger variation of the superconducting gap, and specifically at zero bias. Take a look on the bottom series of spectra. You see that you have also variations of the quasi-particle peaks, but moreover, you have the beginning of gap filling, and this gap filling is completely unexpected for an S-wave superconductor. And so in this paper that I cited, the recent paper we published with Boris Altshuler and Lev Yoffe in Nature Physics in 2014, just 1 month ago, we give the beginning of an explanation of this unusual. Next slide. Andrea, we will go now further on next slides. Next slides. Yes, here, please. So, if you look on this square root 7 by square root 3, simple atomic steps in the superconducting state play a role of Josephson junction, and Professor Hasegawa will speak on that, about this. If you put the magnetic field, next slide, please. Next slide. So here on the picture A, I present the superconducting gap plotted in color at zero field. In map B, I present the superconducting gap at 40 millitesla, and you see that the gap is strongly suppressed at the atomic edges. So each line here, there are 4 lines. Each line, it is a single atomic step. If you raise the magnetic field, you will get additional suppression of the superconducting order. Now, if you subtract from the map B a map A, you will get the map key, which is left bottom part, and you will see that all atomic steps are decorated with vortices. All of them. And these atomic steps are, yes, I'm almost done. This is my last slide. These atomic steps all host these vortices, which is a specific kind of vortices predicted several years ago by Alex Gurevich. And this is not neither Josephson, neither Abrikosov vortices. This is a mixed kind of vortices in which you have a phase gradient which has a jump, partial jump on the atomic step, but you still have a vortex core. And if you raise the magnetic field and you see you do a difference map between 80 millitesla and 40 millitesla, you get a right map, and you see that additional vortices are all sitting on terraces, and all these vortices are Abrikosov vortices. So this system is a very interesting playground on multi-component superconductivity, Josephson network, and all these new kind of vortices you can get. Thank you very much for your attention.
Any questions? Yeah. Well. Okay, you can go here and.
A question from Lara Fatto is coming.
Please, Dimitri.
So, are you suggesting that? Can you go back to the slide?
Yeah.
The zero bias anomaly. Are you suggesting that the zero bias anomaly appears when the underlying the weighting layer is somehow ordered? You have ordered structures here. So you said that in the upper.
I don't see the screen.
Yeah, just a moment.
Could you move the camera, please? Yes.
So in the sense that you say that the zero bias conductance appears when the underlying layer has ordered structures like stripes.
Yeah. Okay. The problem is as following. If you have a very nicely ordered square root 7 by square root 3, you have basically the superconductivity quite homogeneous. And Professor Hasegawa will tell you about this. But however, if you have twin boundaries, as those that are reported as dashed line, or also some stacking fault lines, or also some individual atomic defects, then you get this rise of zero bias conductor. And this rise is not really point by point correlated to the disorder, but rather takes into account a total disorder. You see?
So in the sense they do not only appear on the grain boundaries, they are spread everywhere.
Yes. You have more effect related to grain boundary, but you see, for instance, if you look on the topographic image and you do on the you compare with the zero bias map on the right image, you don't have real complete correlation. Okay, but however, you have it in overall. Okay, but there is no correlation one by one. It is not local effect. It is non-local effect.
Okay, Dima, I have a question. How many bands participate in this superconductivity? I mean, it is one monolayer, nanotube. 2, 3, 4.
Okay, the question is very deep. In fact, nobody knows. No one knows what is superconducting. We believe that it is not a lead which is superconducting, but the interface.
Yeah, okay.
The superconducting wave function in vertical direction is strongly confined in this interface, and this is why every atomic step is Josephson jump. So it is sort of a resonance state. We don't know how many mini-bands are participating. Okay? For the moment, it is not clear. We're trying to get a deeper insight about this, and it is basically the experiments we are running right now.
Okay, so it means that this is a kind of interface superconductivity between
Yes,
lead and silicon.
it is interface superconductivity, we believe, in which the electronic density is given by lead, of course, and probably the phonons are sort of mixed phonons of silicon and lead, but for the moment we cannot stand very strongly about this. The only thing we can show that probably if Andrea okay, anyway, we can show that if you go to slide 35.
35, just a moment.
35 or even 36.
36.
Yes, please. You can see, for instance, here we plot the density of states as the function of position. And you have a jump of the density of state, a jump at the atomic scale when you move from one terrace to another. It means that you have a jump in the order parameter. And for us, the jump in the order parameter, which is continuous wave function, is only possible if you have a barrier. So it means that the single atomic step in this material is a real barrier for Cooper pairs. And it means that it is really Josephson junction, and the superconductivity is really confined to the very topmost layer, atomic layer.
Okay, any other questions? Okay, let's stop
So
with this. Yeah.
in the meanwhile, we prepare Hasegawa. If Yorgos would like to speak in just a moment with Dimitri for the personal question, because we need to move to the other talk, but in the 2 minutes you can just
ask the question. I wanted to ask the question whether, in addition to tunneling, you have any other signature that this thing is indeed superconducting, because it can be an insulating order. For example, a density wave that escapes from the silicon to the layer of lead.
The answer is very straightforward. Please put slide 38.
we don't have any more.
Okay. The answer is very straightforward. We have vortices. Superconducting vortices is a proof of coherence, quantum coherence of superconducting condensate, and the vortices exist in both a striped incommensurate structure, but also in square root 7 by square root 3.
Okay, Dmitri, we thank you for
Okay.
nice talk.
Thank you for organizing all this, and I'm really sorry to not be able to be with you.
Okay, now we need to close the... Okay,
Bye-bye.
thank you very much. Say that. Bye.
Okay, so
Just a moment.
okay, the next speaker is Professor Hasegawa, as you know probably from Dimitri Roditchev presentation. So please,
Okay.
you have 25 minutes plus 5 minutes